All right, gang, Math 6610. Intro, well, just don't know. I don't know why I always say Math 6610 because you obviously know what class you're in, so uh, it's kind of silly. Anyway, intro to ANOVA. I probably told you this story before, and if I have, just fast forward, or if you don't even want to hear it, fast forward. But the first time I taught 6610 was in back in, I think, 2013. And I skipped all what we currently do, or what I currently do in lesson number one, and went straight into ANOVA, two-way ANOVA, some ANCOVAs, repeated measure stuff. And it was about the third time we met, and I could just tell that my students had a completely blank look on their face. And this one student, I'm not going to mention his name, but I recall him, even though it's been that long. Teaches up around Toledo. He said, Dr. Darbo, I have a question. What's a p-value? And another student raised their hand, and keep talking about this central limit theorem and sampling distributions. What's that all about? And another student said, and you talk about a so anyway, I realized at that moment that even though I was teaching a graduate level statistics class, that I had built a class, or I'm sorry, I had built a course on sand, right? So if I go overboard with some of this stuff in terms of building the foundation, it's because of that experience. So moving into lesson number two, intro to ANOVA. It's an acronym for analysis of variance, but the purpose of ANOVA is to examine the equality of group means when we have more than two groups. So we give credit to ANOVA, to one of the great statisticians, Fisher, who was around early 1900s. And the way I like to begin thinking, or at least framing ANOVA, is it's essentially a two-sample t-test on steroids, right? And if you think about any two-sample t-test, it starts, as does ANOVA, with a quantitative variable. And if you want to think about something, if that's the way you learn best, then think about, we start with maybe an ACT score where a mean and a standard deviation uh, are represented. The standard deviation may be known, but we're trying to estimate that. If we partition these ACTs, again as example, into two groups, maybe District A and District B, and we want to examine the mean ACT for District A with mean ACT of District B, then we carry out a two-sample t-test. I don't know if you guys can hear that or not, but my cat is losing his mind. He's just back there just going crazy. Uh, Actually, it's not my cat, it's my wife's cat. So the null hypothesis in this situation, as we've studied previously, is the means are equal against the means are not equal. Now, if we assume equal variances, then we'll run a pooled two-sample t-test. If we do not assume equal variances, we run an unpooled t-test. Ladies and gentlemen, for me, I always want you to run an unpooled t-test. I think as I've dug into the weeds on pooled versus unpooled t-test, even if we have reason to believe that we have equal variances, I prefer to be safe and run an unpooled t-test. So enough of that. And some people disagree with me, and that's fine. They're just wrong. No, I'm joking. Maybe I'm wrong. Who knows? Uh, so ANOVA extends this into what we call K groups. So we'll let K be the number of groups. So for a two-sample t-test, K would obviously be equal to 2. So how do we handle when we get K equal 3, 4, 5, any number of groups 3 or larger? Well, we use ANOVA techniques. So the null hypothesis is that all of the group means are equal versus the alternative hypothesis that says at least one pair of means is different. Now, the first thought is, well, why not conduct multiple t-tests? Well, what this does is it leads to an inflated type 1 family error rate, which we can approximate by taking 1 minus 0.95 raised to the k power, where k is the number of groups. So, for example, if we have 5 groups, we could compare group 1 and 2, and 1 and 3, and 2 and 4, do all these multiple comparisons. And we can see that we can approximate the family-wise type 1 error rate to be about 22%, well, about 23%. So every time we conduct this study with k equal 5 groups, if we approach the equality of the group means by doing multiple comparisons, about 23% of the time we're going to create, well, easy for you to say, we're going to commit a type 1 error, right? We want to control that. We want to keep our type 1 error rate at 0.05, which is our alpha level. We don't want to allow in statistics an inflated type 1 error rate. So what happens when we encounter this? Well, as I say there, Fisher to the rescue. So Fisher, back in about the 1920s, came up with this ANOVA technique that we can use to examine the group means when we have more than 2 groups, and it does not inflate the type 1, the family-wise type 1 error rate. So let's illustrate this with 3 groups. So we can think about population number 1, population number 2, and population number 3. And all these have a mean, and all these have a variance. So what we would do is we would start taking samples. So we would take a sample from population number 1. Obviously, if we're wanting to estimate the population mean, it would make sense to take a sample mean. We'd also take a standard deviation, and we would have a sample size for each of these 3 populations using an underlying probability distribution. Now, again, there's nothing holy about this sample. If we repeated it, we would get a different sample mean, a different sample mean, a different sample mean, a different standard deviation. If we did it again, we get another sample mean, another sample mean, another sample mean. So what we end up getting is we actually end up getting a distribution of sample means for population 1, population 2, and population 3. Well, we model that phenomena using the F distribution. And whether it's a t distribution or a normal distribution or chi-square distribution, within this we create a test statistic. So it makes sense from an F distribution, we would call that the F statistics. Now the F statistic is nothing more than the variation between divided by the variation within. So it's the ratio of the variance between and the variance within. Now, what in the heck do I mean by that? First of all, before we go any further, we have certain assumptions for ANOVA. First of all, our populations must be normally distributed. Unlike the 2-sample t-test, where we don't have to assume equal variances, and if we don't assume equal variances, we run an unpooled t-test, right? Well, for the ANOVA, we have to assume equal variances. And as with any statistical technique, well, most statistical techniques, we assume independence. So what happens here gives you a visual of what really goes on with the F statistic. If we look at this variance within, what we're really looking at is we're looking at the variance within each distribution. But from this statement right here, what are we saying? We're saying that the variances are equal. So this spread that I have from these arrows right here is going to be the same for each of the distributions. That's one of the assumptions. Now, what does that tell us? That tells us that this variance, the denominator right here, is going to remain kind of constant, right? The variance within. We take this cumulative measure that gives us the variances within the distribution from the assumption that we have equal variances, then we can kind of control this. So let's just say we keep it stable. It's not going to move around much. The moving around, so to speak, is the variance between the distributions. There's a variance between those distributions, variance between those distributions, and of course a variance between those distributions. Well, when we have group means that aren't equal to each other, now first of all, imagine this, try to visualize this being mu1, this being mu2, and this being mu3. So they all have the same mean. Well, what would happen with the variance between the distributions? Would be zero because there's no variance, right? So 0 divided by anything is going to give us an extremely low test statistic, p-value equal to 1. We're going to fail to reject the null. But what happens as these distributions start to move away from each other? As they start to move away from each other, the variance between the distributions start to increase, right? Causing this value to get larger. Again, we've controlled for this. This is kind of held constant because of the equal variance assumption. So this right here, the variance between starts to get larger. Well, what happens when in a fraction, if we keep the denominator the same and increase the numerator? Well, the values get bigger, don't they? And as the F statistic itself gets bigger, what happens to the p-value? Well, the p-value goes down. And the p-value going down is more evidence against the null hypothesis, which is assuming that we have equal mean. I don't know why this thing's moving in and out so much. It's starting to get on my nerves. I don't know about you. So what happens? How do we calculate this? We calculate the variances. First of all, let's dive into the weeds a little bit and see what our F distribution looks like. The F distribution as compared to the chi-square distribution or the T distribution has two numbers as its degree. It's tempting to say it has 2 degrees of freedom, but that would lead you to believe that there's just a big old 2 there. It doesn't. It has 2 numbers in the degrees of freedom. It has the degrees of freedom for the numerator and the degrees of freedom for the denominator. In the ANOVA case, it turns out that these are very, very easy to find. Degrees of freedom for the numerator is just k minus 1. Again, k is the number of groups. And then degrees of freedom for the denominator is just n, cap n. N would be the sum of all the sample sizes minus k. So if, for example, we had a sample size equal to 5 from group 1, 5 from group 2, 5 from group 3, we have 3 groups. So obviously the degrees of freedom for the numerator would be 3 minus 1 equal 2. Don't you love it that I'm doing arithmetic for you? And the degrees of freedom for the denominator would be, we would have a total sample size of 15. 15 minus 3 equals to 12. So the distribution from which we draw is going to be the the distribution that we're going to use to calculate the p-value from our F statistic is going to be the F distribution degrees of freedom 2, 12. Now, it's kind of cool in a way. I don't know. I kind of think it's cool. You may not. If we look at this on the calculator, we can very easily take a look at what this distribution looks like. So if you go to y equal and then go over to distribution and then come down to FCDF, no, FPDF, need a probability distribution, probability density function, I should say. Now our random variable will be x, and then we will have our degrees of freedom, which are 2 and 12. Now if I go to zoom and just go to zoom fit, we will get maybe, oh there it is, just took a little bit of time. We will get a graph of the F distribution from which we calculate our p-value using, of course, the F statistic. Now, I can probably give you a little better picture, 0.6. Let's just go back to -1 and see what this looks like. So what's actually happening here is this line, it's not doing a very good job of drawing it, but this line is coming up the y-axis and then coming down and has a right tail. Probably go up a little bit. I don't know, 0.8, something like that. All right. Anyway, there's. I'll tell you what. Let's do this. Let's get into our something we could do here. Um, is we can use a random function generator and create some data. Let's say. So let's just do the random function from the F distribution. Let's do it. What? Let's do it 1,000,000 times. With degrees of freedom 1 equal to 2 and degrees of freedom 2 equal to 12. All right. Now we can create a histogram of these by, so we need to put in the breaks. I always think it's weird that we have to put breaks equals Scott, but we need the frequency. Let's do false so we actually get the bars. Let's let our values range from, I think from the calculator, it looked like 0 to 6. Did a pretty good job of that. And let's run this from, I think 0 to 0.8 maybe. That should do it. All right, yeah, pretty cool. So this is the histogram. So what I did here is I just took from the F distribution with degrees of freedom 2 comma 12, I took 1,000,000 samples and then just looked at a histogram. So this gives you a pretty good idea of what the probability density function would look like. I mean, in statistics, we call that the sampling distribution. All right, sorry about that. I just thought that's kind of cool. All right, to be able to do that. So again, we're making our calculations within this distribution. All right, so what's up with this F statistic? Now, in the next video, I am going to actually demonstrate this, and then we're going to import our data into R and show you how we make the calculations there. But what happens is calculating the F statistic, again, it's the ratio of the variance between over variance within. A student one time asked me, he says, well, I always forget, is it the variance between over within, or is it within over between? Well, I just remember between comes first. B comes before W. So that back in the day, that's the way I remembered it. So it's the mean squares between divided by the mean squares within. The mean squares between is just the sum of squares between divided by the degrees of freedom between. And the mean square within is just the sum of squares within divided by its degrees of freedom, which we call degrees of freedom within. So this up here, this whole thing is called the mean squares between, and this whole thing is called the mean squares within. This part is called the sum of squares between. This is called your degrees of freedom for the between, and this is called your sum of squares within, and this part is called your degrees of freedom within. So in the next video, I'm going to run through a calculation, then put it into R and see what's happened. Then we'll eventually get into testing assumptions and writing up results. And so that's the game plan. All right, gang, all I got.